Okay, so hi everybody. Today Alon Dogon will talk. He will prove Naimark's dilation theorem and explain a bit about C-star algebras and other dilation theorems and how all of it is related to quantum information and specifically non-local games. Thank you, Alon, for coming. The floor is yours.
Thank you. Okay. Thank you, first of all, to Michael and other organizers for putting all of this together and giving me the opportunity to speak. Yes, so Michael already gave more or less the introduction to what my goals today are, but let me repeat it briefly because I basically have two goals today. The first one, which is something we already talked about in this seminar, and Michael promised a few times that we will talk about at some point. Well, the time has come. Recall that when measurements in quantum information theory, we had many different versions. That was Cyrelson's problem, but at the basic level, even when you have just one system, we defined what was a POVM to be some set EI of positive operators on a Hilbert space that sum up to the identity. And this was like the more general notion of measurements, sometimes I guess called sub-measurements or something like that. But the more specific and nicer way of measuring things is using what's called a PVM. And this is a much simpler notion of just sort of a partition of the identity in a non-commutative sense, if you will, where we choose n mutually orthogonal projections in a Hilbert space that sum up to the identity. Okay, so these are a priori two different notions. And today I want to talk about how you can basically obtain measurements done with POVMs using actually measurements of PVMs. And this will be the goal of this lecture, and we will also it will be an explicit way, but I would say that is some kind of my secondary goal. I would want you to understand the statement, but I mean, this proof is not hard, and there are other ways. What we will use is called Naimark's dilation theorem, but there are also, it has its faults, and there are also more sophisticated ways of doing this, which is more relevant in quantum information. However, my goal today is kind of mainly to set the groundwork of relating Cyrelson's problem, that is quantum mechanics or information theory, to a more, say, pure mathematical language of C-star algebras and completely positive maps between them. And this is important because this is basically historically how people related Cyrelson's problem to the famous Kohn embedding conjecture. And we won't talk about it this time, but in general, I want to introduce this language and kind of show you how to translate objects between these two areas. But
I'll just motivate you a bit more to listen closely to Alon, because he will probably talk again with Daniel, and they will prove to us the equivalence between Cyrelson's conjecture and the Quep conjecture of Kirchberg. And to understand that, we will need this framework of C-star algebra. So also, indeed, it's a good place to start.
Yes, indeed. Thanks for the advertisement. But of course, I know that specifically in our university, this is less of a prevalent area, and especially I think the participants of this seminar are not so familiar with this language. So I want to this is a vast field, but I want to like focus on relatively simple, as simple as possible and as concrete as possible terms. So I will work with infinite dimensional Hilbert spaces. I mean, everything will be relevant, but for those of you who prefer, you can always think about finite dimensional ones if you prefer. But before we get into the sister algebra part, which I just want, just for not to make you wait, I will give the statement of Naimark's dilation. And I mean, there are many ways to state it, and somehow the people in quantum information state it differently than how, I mean, the statement in quantum information is a bit different on surface from the one maybe found in some operator algebra books. But this version is taken from a paper by the authors of MIP star equals RE in a, I think, newer paper, is it? This quantum low degree test paper? Which is...
Okay, so there was this problem with the original paper. They published a fix. This fix is an additional paper, and this theorem is taken from there.
Yeah, great. So let's look at it slowly. So I start with two commuting positive operator measurements, and as written here, x, y denote questions and ab denote answers. And so for each for each fixed x, we get a POVM. Okay, this is, I assume you understand. But by the way, I didn't say, but ask me anything. And we fix a state in the tensor product. So we are talking here about the tensor product model. Okay. Then, by the way, before I continue, maybe in this statement, you should think only about finite dimensional Hilbert spaces, because it's also true for infinite dimensional ones, but it's not so relevant. And so again, I have HA and HB, which are the Hilbert spaces Alice and Bob have their qubits from respectively. And then I say that there exist two other Hilbert spaces, which is A, H, which an auxiliary. The aux here is shorthand for auxiliary. So it's the auxiliary Hilbert space of Alice and an auxiliary Hilbert space of Bob. And I say that, and there are two states, so unit vectors in these spaces respectively. And okay, before we get to the PVM, okay, so what will happen is the following: we will basically date, and okay, we want to pass from a POVM to a PVM, and what happens here basically is that in this passage we need to add kind of redundant qubits in a sense, but not really redundant. I will maybe remark on that a bit. And basically we take HA. Sorry, I want to use this way. We take HA and then we tensor it with HA aux. So we kind of dilate it a bit. And we have HB too. And we add some redundant qubits to it too. And then I promise you that you can find a projective measurement. Here it's a PVM acting on this guy. So here is not A, it's B. And here it's A. And it's A, this is YB. So I have projective measurements on the dilated Hilbert spaces. And also I can take my state from the smaller tensor product. And also this formula basically says that we take C and and we tensor it with the states we chose, and kind of this, the thing is that C hat is kind of, in brackets, a pure tensor in the sense that we only took the information of C and then tensored it with two other states, and we didn't take some new linear combination in the larger space. this C hat is decomposed. The main information in C hat is inside C. And with respect to this C hat, we see the claim is that these probabilities we get with respect, this is a PVM, are the same as the probabilities we originally got. This was a POVM. Okay, so again, this says that we can add some extra dimensions and find projections on this larger Hilbert space, such that the generated probabilities are the same as the probabilities we had before. And
this is for every A and B and X and Y, I guess.
yes.
The addition is the size of the addition is independent of psi.
So good point. So I didn't write it, but the dimension of these HA ox and the dimension of HB ox is equal to the number. I think it's bounded by the number of questions times answers. Questions, this times number of answers.
It's not dependent on the dimension of HA and HB?
No, it's only, I mean, the larger, okay, there are two things. I say that this dilation element, this dilating Hilbert space, the one you take a tensor product with, is only depending on the number of answers and questions you get. But of course, I tensor it with the original Hilbert space, so I kind of multiply it by this factor.
Okay, yeah.
Okay, makes sense?
Yeah.
Cool. I mean, yeah, so this is kind of more formulated in a language of, okay, using tensor products and think. I have a question in the chat. Do the auxiliary states depend on psi? So in this case where we have like, so yes, in this case, no, wait. No. No, they don't depend on which psi you use. It will be the same for, I guess. No, it doesn't depend on which. No, it doesn't depend. I really hope we will see it in the end, because yes.
I just want to say that the main point here is that you can assume like the goal will be to say that without loss of generality we use PVMs instead of POVMs, like that.
Yes.
This is like the for anything related to the distributions that achieved here, which is exactly the inner product written at the end. We can assume that we use PVMs by dilating the space enough, like that.
Yeah, but Itai's question is in the chat is relevant because yeah, it doesn't matter which auxiliary states I choose, but at the end of the day, it doesn't matter. I mean, for example, for the definition of CQ, CQC, and taking like the quantum value of a game, indeed, this doesn't matter because we just say that we get the same set of correlations, right? Using POVM or PVMs, it will be the same. But okay, are there any more questions about this? I messed up this slide a bit, but I hope it helped. Okay, but kind of now I want to.
Alon, I'm sorry,
yes.
how far does this independence of psi go? So can you actually take the last words in the second line, push them down to the fifth line?
Which last words in the second line?
Yeah.
Joint state?
So no, psi, you don't define psi there.
Okay.
And then you only say you've defined these auxiliary spaces, and then
yes.
such that for every psi, this equality holds.
Yes, I think even you can take, no, these guys are important because
No, I understand.
I
but
mean
can
only
you
the
push-
number of questions. Yeah, so I
no,
can
you
take.
push the psi down? There is no ignoring psi for the moment and only mention it. Right? Can you push this down?
I mean, now I cannot. I can only draw. But yes, as Nati said, okay, maybe a better formulation of it would be, the data of psi will come only after I say these Hilbert spaces and auxiliary states exist.
Okay.
But I mean, kind of after we see the more operator algebra, I guess, formulation of this, these auxiliary states and everything, it's kind of just a bit complicating the fact that we just have an embedding of HA inside this larger dilated space. But we will see this in more clarity in a purely mathematical field later. Okay, but I think we can move on to the fun part. Study of C-star. So now we are moving to like pure more functional analysis. But okay, so maybe a bit of history I will just say, but before that, the hierarchy of fields is that the study of C-star algebras is a subfield of the study of operator algebras. And maybe I'll add another one, which is the study of von Neumann algebras. And this is also a subfield of operator algebras, and it has many relations between, we have many relations between the field of von Neumann algebras and C-star algebras, just as there are relations between topology and measure theory. And these are, everything is a subfield of functional analysis, but maybe functional analysis is a big field, and many of you are very familiar with it. But okay, so generally functional analysis studies algebraic objects, so say vector spaces, algebras, groups, but we endow them with analytic structure, norms, inner products, and further things. But many times, okay, you need some compatibility between the structures, but we know, for example, the notion of a Banach, okay, the notion of a Hilbert space is extremely rigid, right? Once you, I mean, the dimension determines everything, but we have the theory of Banach spaces, which, okay, you need a vector spaces and a norm, and there are many pathological examples where maybe the vector space looks simple, but the properties of the Banach space are very, what I'm trying to say is that the study of Banach spaces and trying to classify them is extremely hard. But on the other hand, when we restrict ourselves to C-star algebras, one of the main features of the theory of C-star algebras is that the algebraic structure completely determines the analytic structure. Okay, we will see it in a statement in this form later. And okay, let's dive into the definition. Okay, but before I give the definition of a C-star algebra, let me talk a bit about the the algebra of bounded operators on a Hilbert space. So what kind of structure does it possess? Okay, so again, now we are thinking of infinite dimensional Hilbert spaces. This is the interesting case. First of all, it has an algebra structure, so it's a ring with a scalar product over the complex numbers. But we also have an involution, which is taking the adjoint, and it plays well with the algebra structure. What do I mean by that? There are a few axioms, but you know every one of them simply by thinking about the transpose conjugate of a matrix, right? For example, one of the important ones is asking that the adjoint of this reverses the order. Okay, so we have an adjoint operation. And here is the analytic structure, which is a norm. We have the operator norm, which we know and love. And this norm is nicely behaved in the two following bullets. The first one is defining, it says that it's what's called a Banach algebra norm, but it just says that, okay, this norm is complete, meaning that BH as a vector space, as a metric space in this norm is a complete metric space. And also it has a submultiplicativity condition, which is easier to verify. And also the adjoint operation is isometric with respect to this norm. Okay. Finally, it satisfies the most important identity of C-star algebras, which is called the C-star identity, which is basically saying that if you take the norm of T star T, you get the norm of T star T will be the same as the norm of T squared. Okay, and this can be verified for the operator. Okay, why did I list these structure axioms, say on BH? All of them are relatively easy to verify on BH, and thus we can look at closed star subalgebras of BH. What do I mean by that? A star subalgebra is just a subalgebra of BH closed for the adjoint operation, and closed, I mean in the operator norm, right? That it respects the topology defined. And okay, for the purpose of this lecture, we will also ask for it to be unital, meaning that it contains the identity operator of BH, but in general, it's not required. But for simplicity, we will require it. And why these things are interesting? These conditions exactly ensure that all of the structure from the previous slide passes down to this subalgebra, right? It's closed, so it's complete in the induced norm. The norm satisfies all the identities, and etc. Okay. But you might ask me, okay, that's nice and all, but why are these star subalgebras of BH so special? And why are these axioms the specific ones which somehow specify the important aspects of them? So turns out you can also define a C-star algebra axiomatically, meaning it sums complex algebra with the norms satisfying all the previous conditions. And so if you take such an algebra with all the previous conditions, I don't claim, but Gelfand, Naimark, and Segal proved that you can represent it on a Hilbert space, meaning that this abstract structure has a faithful representation acting on some BH. Okay, so essentially, looking at closed star subalgebra of BH is the same as looking at this axiomatic theory of C-star algebras. Okay, this is kind of like if you will, a Cayley theorem for finite groups, where a finite group is the same as studying subgroups of Sn. Okay. But if there are, still this maybe for those who like applications, this is not so clear yet why this is important. But let's say von Neumann himself, I think, defined objects that are similar to these, first of all, to kind of try to formalize quantum mechanics. Like from the start, these objects were studied because of quantum mechanics, but then Gelfand studied these more because he was interested in representation theory of infinite groups. I mean, these objects basically are the ones, if you want, are the ones which encode all the representation theory, unitary representation theory of the group. And so there were a lot of...
Do you know how difficult this theorem is?
How difficult it is? It's not difficult.
It's not difficult.
I mean, it's not trivial, and it's, I'm sorry, it's not difficult, but it's absolutely beautiful and non-trivial. I mean, to convince you that the proof works, it's not hard. But what's so beautiful about this theorem is that it generalizes also many things you might know. For example, the positive definite functions on a group and how you use them to relate to representations are manifestations of this theorem. And
What, Bochner's theorem, this kind?
Bochner's theorem, or Bochner, yeah, all this abstract harmonic analysis is much better understood once you have, I mean, this is not just a theorem, it's a construction. It gives you a specific construction.
So actually, given a C-star algebra, they'll construct for you a Hilbert space and
Yes.
show you how, okay.
I can construct a Hilbert space and it gives much more. It relates what's called states of the algebra to representations of the algebra. So it's not just a construction, it's even a philosophy, if you will, of saying for groups. Many of you would know that studying representations of the groups is the same as studying the positive definite functions. Many properties such as property T, amenability, everything can be which are representation theoretic, can be formulated with positive definite functions, and this is kind of taking it even a step further. But we will basically kind of see a proof today to this theorem in the sense that the dilation theorem I will prove is so general that it also includes the essence of this construction. And I hope we will get there, but let's continue. And it was abstract. Let's see a few examples, really simple examples. So I said, okay, any BH will be a C-star algebra. In particular, you have finite dimensional ones. And maybe I'll remark that a finite dimensional C-star algebra, this is the same thing as taking a direct product of certain matrix algebras. So you can take direct product of C-star algebras and get a C-star algebra, and all the finite dimensional ones are of this canonical form. But the basic building blocks are matrix algebras. And these are the finite objects. And you can also, okay, this is also a simple example. If you have some subset of BH, you can always look at the star algebra it generates and close it off in norm, and you get some C-star algebra. And maybe I'll remark here for the group theorists, it's not important for the lecture. If you have some representation pi of G inside some unitaries of H, a very important C-star algebra associated to this representation, C-star pi of G, is just the C-star algebra generated by the image. Okay, it's kind of just taking all the multiplications. This is an algebra and closing it off in norm. All the linear combinations. Okay. The third example is also very interesting and relevant. The third example is the most relevant and interesting for today, because this will relate us to POVMs. The third example is another finite dimensional C-star algebra, which is implemented on just this C to the N. So what I say here is look at it in two ways. You can view it both as, say, the L2 space of an N element discrete set, but you can also view it as continuous functions on this discrete set. Continuous functions it will be more clear why I say continuous, not just bounded whatever in example 4, but this is what conceptually we think about. And I need to tell, okay, what is a C-star algebra? It has to act on some Hilbert space.
Sorry, where are continuous functions here?
So when I denote C of something, it means continuous functions on this thing. So here it's continuous, a discrete N element set.
Yeah, so everything is continuous.
Continuity is
Okay, fine.
Yeah. It's trivial here. In 4, it will be more relevant.
for the next.
In the same way that being L2 is
is just nothing.
But
it says
it defines a norm or something, but fine, okay.
Exactly. So here you will kind of take what's
Oh,
called.
and here it's the infinity norm, I guess.
Yeah, it will be the infinity norm, but remember that when how I define the C-star algebra now, I wanted it to be the operator norm on some Hilbert space. So I need to tell you how A acts on H, right? I mean, it's the same thing, but I treat them as fundamentally different objects. So a function in F will act on H just by pointwise multiplication, right? I take some vector C and look at the pointwise multiplication, and this is, I mean, the function F, yeah?
No, I just said that now I see what you're going after. Okay.
Yeah, this is nothing other than just looking at diagonal matrices, right? This multiplication. In fact, the general spectral theorem will just be saying that basically all unitaries can be reduced to kind of a continuous counterpart of this example, which is the next one. But for the next example, which I won't go into details, but you can think, instead of looking at n discrete n element set, let's, for example, look at a continuous object such as the interval. We can look at the continuous functions on it. And here it will act on L2 the same way, just by pointwise multiplication. And like a fundamental inequality, if you want, is that the L2 norm of F times G is less than the sup norm of F times the 2 norm of G, right? So this, you need to check that this action is somehow faithful and that the supremum norm is the same as the operator norm. But basically, this kind of multiplication operator construction works for any compact Hausdorff space. But notice that example 3 and 4 are very special in the sense that they are commutative C-star algebras. I mean, the interesting theory of C-star algebras manifests itself because pH is non-commutative. And here we looked at diagonal subalgebras, if you may, which are commutative by definition. But any questions about the examples? I'm going quite slow, so yeah. Let me try and hurry. I will need to hurry up a little bit, but yeah. Okay, now we jump back to the abstract definition. And what are the morphisms between C-star algebras? This will lead us to the next topic, which we want to talk about. So if you have two star algebras, a requirement for a morphism between them, first of all, I will want it to be linear. Okay, so it will be, these morphisms will be called star homomorphisms, where the star is for the adjoint operation. So because these are algebras, I would want them to be multiplicative. I would want them to respect the adjoint operation. And also I will want them to preserve the unit. Okay. Now, some of you may be thinking something's fishy here because I didn't say anything about the norm structure, right? I mean, A and B have equipped operator norms, and this was part of their fundamental definition as analytic algebras. Here I just look at an algebraic homomorphism, right? Turns out that one of the first results you prove when studying such objects is that any star homomorphism is automatically operator norm decreasing, contractive. And so any homomorphism will be continuous. It will be a bounded operator of norm 1. And further, if it is injective, then it is isometric. So here, like the operator norm of 1 passes to the other. And is at least the statement of the proposition clear? This is just a phenomenon in C-star algebras where the algebraic structure completely determines the norm.
Are you saying that the second part follows from the first one, or these are just
yes? No, the first one is a definition, right?
No, I'm talking about the proposition. It has two sentences. Does the second one follow from the first?
Yes. But
we follow by multiplying by the unity.
Sorry.
Doesn't it simply follow? Simply take the function, take the element.
Oh, just because. Okay, because if it is injective, it is also yeah.
Can be. But you need to say that the image is also a sister algebra. Right? Yeah. But that requires a small extra algebra. But yeah, great. Nati, what was your thought?
No, that doesn't it simply follow by multiplying by the 1a?
By 1a, what do you mean multiplying by 1a?
So what do you get when you you know the pi a b equals pi a pi b? What happens if a is 1? Doesn't this give you?
I'm not sure, because I don't think so, because in none of the axioms for a star homomorphism did I mention the norm. I mean, okay. This just equals pi b. I'm not sure.
Okay.
Yeah.
So
it does,
but proposition carries some.
It carries quite a lot of substance. I mean, it's well known and everything, but the proof requires something, and it basically requires some kind of the spectral analysis kind of, because basically what proves it is what's called the spectral radius formula, which says for normal operators, the norm can be computed that if a star a equals a star, then you can compute this norm using some limit of the following form.
Okay.
This somehow enforces the contractivity.
Which is, that's completely analogous to what we do in matrices, right?
Yes, it's absolutely analogous. Just
matrix is normal, and then this is the power method to get the spectral radius of the matrix.
And actually, if I remember correctly, the whole theory is like this. It's like I tie your hand behind your back, and you're not allowed to use vectors, but you can regenerate everything by the tricks that you actually already know from matrices.
Right.
Yeah, there are many things which patch from matrices to infinite dimensional setting, but some things still break down and are why these things are interesting. I mean, such a direct sum decomposition into simple. I mean, beforehand I said that in a finite dimensional setting you have some decomposition theorem. This is not true in general. Like to be able to decompose into some irreducible parts of the algebra. But you're absolutely correct that the spectral analysis aspect, like it passes to bounded operators quite nicely. Yes. But okay, but once we believe this proposition, this kind of leads us to not a problem, but like there are two sides of this phenomenon. So because this is very rigid, for example, you have from algebra the first isomorphism theorem, and many purely algebraic theorems still hold, like which you wouldn't expect for Banach spaces or anything like that. It's a lot of automatic stuff happens, but this also makes this category. This makes this notion of sister algebras and star homomorphisms a very rigid notion. Like you do not have too much flexibility. And people with the time defined a different type of morphism, which is what I will go to now, which somehow captures this flexibility. And the goal of this lecture will exactly be relating the two types of morphisms. But I won't touch upon this in this lecture, but because sister algebras are so algebraic in their nature, it makes them amenable to tools from algebra, such as K-theory, representation theory, and many such things which are purely algebraic pass to this setting and are very strong in classifying the structure. But that is a topic for a whole course. Okay, I want to now, what I want to now is go on to define what the main player of our talk, which is UCPs, unital completely positive maps. But before that, I need to give a small remark about matrix algebras over a C-star algebra. Okay, so, I mean, once you have a ring, you can always consider matrix algebras over it. And now I want to kind of give you a more concrete sense of what this means in C-star algebras and also convince you that this is a C-star algebra in itself. So note that given a C-star algebra A, we can consider the matrix algebra over it. So MNA, this is just matrices with entries in A. And I claim that this is also a C-star algebra when you view it as acting on the direct sum of the original Hilbert space. So what will we do? I mean, you have some matrix, A and N. It will act just by vector multiplication you know from high school. I think that in your generation they taught in high school, I'm not sure. But yeah, anyway, you know the formula, right? The point is that because A acts on H, it makes sense to multiply A with C, okay? And so we can indeed view this matrix algebra as operating on this direct sum of n copies of H, and it will also be closed in the norm. Okay? And so it has some representation on a Hilbert space. Okay. And okay, I will give you another realization of this algebra in a second, but just for you to recall, given two operators on some Hilbert space, we compare them just by comparing their matrix coefficients, right, under all vectors. But before moving on, this is, I think, important to mention. Notice that this algebra can also be identified canonically as a tensor with MNC. What do I mean by this? This is a tensor product of algebras. Right, there are both vector spaces. You can take the tensor product as vector spaces, and then you have a natural operation of multiplications of pure tensors. And I won't remind the definition now, but maybe, I mean, let me elaborate maybe a bit more on how this isomorphism works. And so if you have basically this works because also we have that this space, okay, so this guy acts on this, right? It acts on the direct sum of n copies of H, but this Hilbert space can also be viewed as H tensor product with C to the n, right? And of course A acts on this, and Mn is the full algebra which acts on this, and we can take their tensor product which acts on the tensor product which is H to the n, and then like this is something you need to convince yourself, and these actions give this isomorphism between the algebras, but maybe I'll write it explicitly. So if you have an element here, A tensor some P, where P is a matrix and A is just an element of the algebra, this corresponds to the matrix AP11 till AP1n, APNN, APN1, so on.
Alon,
right?
I think
Yes.
I think that when I talked about tensor products, I talked about the
You already talked about this? Yeah, this is the Kronecker
product. And
yeah, this is exactly
this
Kronecker.
Yeah, exactly. So we at least saw it when I introduced the tensor products of Hilbert spaces.
Great. I just want to make sure that you are all not going to, you can complain later, but that you are not sure what the matrix algebras over over sister algebras, but this is like just think of the simplest example, right? Matrices over matrices is just matrices in the multiplied dimension. But yeah, okay. I'm pretty sure you are already familiar with this, so I won't elaborate much more. And I think I will finish with the definition of a UCP map and give you a break. And just because you are still these MNAs are still hot in your mind. So what is a unit of completely positive? A map between two sister algebras is called UCP. If for each n, when I look at these matrix algebras over A, I can look at also phi induces a map on these matrix algebras. How? Just by this. So phi n will take some matrix over A to just evaluate, just applying phi to each entry. And I want phi n to be a positive map. So what that is, if you take a positive matrix here over A, then so is phi n of A. There's a small subtlety here. A positive map just between two algebras takes positive elements. And positivity, you know, because these are all operators, you know what are positive operators. And the extra adjective of completely means that when I look at the dilations of phi to these matrix algebras, it is also positive. I mean, you might think this is automatic, but it is not. And this is the extra, assumption of what's called completely positive. And I will also assume that the unit goes to the U. So I think I will now give the break and let you digest this slide, and I'll be here to remind anything or answer any question. Alex. Okay. So, everyone is here. Most of you are here. Okay, let's continue after the nice intermission. Ken, where are we? We defined UCPs, and just to remind you, we required the positivity of all the maps induced on the matrix algebras between A and B. Okay, let's move on to, again, examples. Here the list is not long, but it's very interesting. So first of all, the trivial examples of UCP maps are star homomorphisms, right? Because if we had a star homomorphism, then you can check that the map we defined on the matrix algebras will itself be a star homomorphism. And star homomorphisms always preserve positivity. I mean, if you have a positive element, then standard C-star theory shows that also the image under a star homomorphism is positive, and so automatically.
Alon, I think this is easily seen because yeah, because every positive element is of the form A star A. Yeah, and being of the form A star A is preserved under star homomorphisms because of being preserved under star action.
Yeah. Because like there are two ways to define positive elements in general, right? When you have an action on a Hilbert space, you can ask the matrix elements to be positive, but this is the same as asking for there to be like a square root. Like if you are of this form A star A, then you are positive, and vice versa. And then it's easy to see that star homomorphisms preserve positivity. And what's important is that being a star homomorphism lifts up to these dilated maps. Okay, these were like very rigid morphisms. Now we will see that POVMs can be interpreted as UCPs. And this is the main point. This is how we relate back to Naimark's dilation theorem, because we will prove a structure result on on UCPs. And as a result, we can interpret this structure theory for POVMs in particular. And this structure result exactly be like giving all other possible examples of UCPs. But maybe for the group theory experts here, I will just mention that a UCP of a group, UCPs generalize very naturally positive definite functions. Like this positivity assumption is very much reminiscent of the positivity assumption of positive definite functions on groups. And so we will also generalize the results about those. And this is what's nice about this theory. It's kind of still specific enough where you can do computations, but it also brings together many fields. But now let's talk about and prove the relation to POVMs. So what is the proposition? Given a Hilbert space, oops, wait a second. Yes. Given a Hilbert space, so the following are true. So first of all, what is a PVM? I claim, so PVMs are just a collection of mutually orthogonal projections, and this canonically defines a star homomorphism from this C-star algebra. So you remember one of our important examples was interpreting these finite dimensional vector spaces as a C-star algebra of diagonal operators. And I claim that any PVM extends to a star homomorphism. So here it will be a star homomorphism assigning the ith basis or basis projection to the chosen projection. Okay. By the way, this I won't prove because it's quite easy. I mean, when you have a set of mutually orthogonal projections, their algebra structure is nothing. The multiplication of any two different ones is trivial, and they sum up to the identity. So this first clause is quite easily seen, unless someone wants me to elaborate a bit more. The second clause is what will be interesting, is when we replace a PVM by a POVM. Then I claim this defines not a star homomorphism, but a UCP map from this C-star algebra to BH by the same rule. Okay, and of course, like you extend it linearly, right? Phi of sum of lambda I EI will just be the sum of lambda I phi EI. Okay, so is the statement of the theorem clear? Okay, great. I assume it is.
I'm
now,
a bit confused. Maybe
yes.
I'm not confused, but maybe something to point out is that the EIs don't commute naturally. So clearly this is not what?
No. You mean the big EIs?
The big EIs, the
yes.
small EIs do commute always.
Yes.
The big EIs not necessarily commute. So
exactly.
clearly this is not, in general, not a homomorphism. But you say it will be always a UCP map. Okay.
Exactly.
I'm just pointing out the fact that the second example cannot be a homomorphism.
Absolutely. But you can kind of guess that it will be a UCP map because POVM is kind of a positivity assumption, right? You have a positivity assumption on the images, and this will translate to a positivity assumption on the map. But there is, so let's say what is absolutely clear here, right? I mean, what are positive elements of C to the M? Let's first prove that phi itself is a positive map, right? The complete positivity is positivity of all dilations. Let me first convince you that phi itself will be a positive map. Why? Because if this sum lambda I EI is positive, this is if and only if any I lambda I is positive, right? I mean, you can check that in this very simple C-star algebra of C to the M, positive elements are exactly positive functions, if you will.
Yeah, we stated it when we talked about finite dimensional matrices that I define them to be such that their eigenvalues are non-negative, but you just mentioned that the lambdas are the eigenvalues, right? These are diagonal. These are already diagonal.
Yeah, you can see it in this way indeed. And then you see immediately that so how does this linear rule extend? We take so assume this guy is positive. Its evaluation will be the sum of these guys, but the sum of these guys is just the sum of lambda I ei, and this is a sum of positive operators with positive coefficients, which is positive, right? So I convinced you now, I hope, that phi maps positive elements to positive elements, at least. The problem is lifting it to all dilations, and this will actually be a phenomenon generally because of the commutativity of C to the M. Any positive map from a commutative C-star algebra to BH will automatically be completely positive. So this proof is a bit more involved. I will write it out, but I don't think I will have enough time to explain why explain it well. But again, this is a theorem of Steinspring. This is not the next theorem will also be of Steinspring, but any positive map phi from C to the M to BH uniton is UCP. So why is this? So the proof goes as follows. So I wrote it like this. Okay, we want to consider phi n, which goes from Mn of C to the M as a C-star algebra to Mn of BH, right? But let us use this canonical identification we had before and identify this guy as C to the M tensor product with MNC. MNC, right? This we have. And so any positive element, so in general, it's some non-pure tensor. I will say just sum over I of some, what did I denote here? It will be just delta I tensor sum PIs, right? Where PI are from MN. These delta I's, it was the EIs from before. Yeah, maybe I'll denote EI. So it's better to be consistent. So EI are these N projections which span C to the M. So because we have this, we can decompose every vector in the following way, right? And also, PI are positive matrices, assuming that this guy is positive. I mean, what I'm trying to say is that once you know that this tensor is positive in this tensor product, it will say that PIs are positive. And why is that? Is because there exists a homomorphism from C to the M tensor MNC to the ith component. I mean, this projection to ith component. This projection onto the ith component with respect to the basis of C to the M is a star homomorphism, and so it will preserve positivity, right? So if you have a positive element, I can project to the ith component, which is this matrix PI, and it will also be positive.
Alon, let me give another way of thinking about it. Like,
many ways
CM
of it.
tensor MNC is just the set of all block diagonal matrices with blocks of size n by n. This is just C to the M tensor MNC. And saying again that this has only positive eigenvalues means that every block has positive eigenvalues.
Exactly, that might be a better
And this means that, like saying that all the blocks have positive values exactly means, positive eigenvalues exactly means that all the PIs are positive. No negative, actually, everything, but.
Yeah, and so you agree with me that because C to the M is such a nice commutative C-star algebra, I can say, I can have such a decomposition. But then, okay, so PIs go from MN, but then how does phi to the N act on this positive element, right? By definition, it will be, okay, sum of I to 1 to the m, phi of n of phi n of this EI tensor PI. But this will be, I mean, how we define phi n will just, it will just act, let phi act on EI and tensor with PI, right? Because maybe I'll, before I explain this last equality, let me slide back to the definition of the UCP map. This guy, phi n, you can also interpret it as phi tensor IDN, right? Where IDN is like the identity operator on MN. And I mean, this is, okay, I am going through this fast, but this is how basically it's defined. So in this tensor product notation, you get this expression. And now, because we, okay, now by assumption, we know that phi of EI.
Alon, just can you move back one slide?
Sorry.
I think there was a small notation that, okay, you lost the n. I think this is an important point that at least was.
Yeah, exactly. Like
phi n acts on EI tensor PI exactly as phi acts on PI, and then identity
and on the other side is nothing, exactly. But
yeah, great.
Now, yeah, exactly, good, Michael. But now it's already kind of clear why the assumption of positivity of phi implies the positivity of phi n, right? Because this we assumed is positive, and PI, I just convinced you before, is positive. So also the tensor product of them is positive, and the sum is of positive stuff. Okay, and this establishes the proof. I mean, in the commutative, you can also use it to prove. You can also use like a similar partition of identity argument to prove that this is true for any commutative C-star algebra, but in this very specific case of C to the n, the proof is quite straightforward. But okay, this is, I think this is okay unless anyone has a question. The main point again is, yeah, sorry, Ka?
Yeah, so what you, so are we done? I mean, okay, I accept the fact that every positive map
yes,
between C to the M and BH is positive. Does it finish the job of showing that the map that we are interested in is positive? Are we done?
So I remarked before.
You mean UCP, right? But positive is a weaker
UCP,
notion.
sorry. Yeah, I mean UCP.
Yeah, so yeah, now you believe me kind of a C-star algebraic fact that any such a positive map will be UCP. We are done now because of like work we did in the previous slide. I said that this assignment, if you expand it, you get exactly like a sum of these EIs.
Right. Yes.
These EIs were the POVM. And we assume they are positive. So this is automatic.
All right.
Okay.
So basically, so basically positive and UCP is the same in this case.
In this scenario, exactly. But in this commutative scenario, it is the same, but in general, it is not true.
Yeah.
Cool. Now we are moving towards the structure theory of such UCP maps. Again, we realized our problem is kind of a specific case of talking about UCP maps. And then a dilation theorem is exactly a method of passing from UCP maps back to star homomorphisms. So this exactly corresponds to passing from POVMs back to PVMs, right? Because POVMs were the star homomorphisms whose domain is this commutative C-star algebra. So there are several ways of formulating, and many people do it. Actually, I think I read a bit, but I couldn't really understand. I mean, there's like these notions of quantum channels, which people like to talk about, and they are by definition like UCPs, and there are a few dilation theorems along the history. However, the following one is, I think, one of the most powerful, general, and also clearest one, which is called Stein-Springs direct dilation theorem. Okay, but before I give the theorem, I want to give you an example, which will basically be all examples because of the theorem. Take a star homomorphism pi from A to BH. Okay, A is some C-star algebra. Now choose a projection in BH. Okay, onto some closed subspace K inside H. We can now look at the map defined by taking A, evaluating it under the homomorphism pi, and then compressing it with respect to T. Okay, and this lands inside BK. I claim, I won't show it now, that this is a UCP map. Yeah, this is kind of maybe not clear when you first see it, but once you try to write it out, it's quite clear, because again, positivity is just some game with the matrix coefficients. But what I'm telling you here is, given any star homomorphism, I can kind of ruin it by projecting onto a subspace, and I won't necessarily get a star homomorphism, but it will be a UCP. It will retain the positivity, strong positivity properties of pi. And now the next theorem exactly says that this is all possible examples. And this is the main, I think it's the main theorem / tool of or philosophy of the talk, which reads as follows. Any UCP map, and A here is some C-star algebra, any C-star algebra, into the bounded operators on a Hilbert space, which is UCP, I can find a larger Hilbert space, H hat, which contains H under some isometric embedding. And I can find a star homomorphism into this larger Hilbert space, such that this UCP map will be exactly of the form from the example, will be the compression of pi with respect to with respect to the projection onto the smaller Hilbert space. And so maybe you are welcome to ask me questions at this point, because this is important. But I will just remark that this generalizes the fact that, for example, what Nati asked it before, the Gelfand Naimark Segal construction, it is a particular case of this one, when UCPs are just states. And also, and the even more particular case of that is just this theorem that positive definite functions give representations of a group. Yes. But are there any questions about this statement?
I think, Alon, something interesting about this point is that even if the original H was finite dimensional, the new H hat may be infinite dimensional.
Yeah, this is something actually
like you need to dilate very much sometimes.
So it depends on
seems
A.
Yeah, clearly, right. For some A's, you will need to dilate, infinitely dilate, which, because this sounds too good to be true if H hat had some restrictions on it, but actually H hat can be very, very, very large.
So it has a restriction it has, which is also prevalent for what I said about Naimark's dilation theorem in the specific case where everything is finite dimensional. We do have such a bound just by how we construct H hat. We will take some kind of tensor product of A with H. So in particular, when A and H are finite dimensional, you do get something finite dimensional. What you are referring to is somehow when you are talking of groups, infinite groups, and then A itself will be an infinite dimensional algebra. So indeed,
yeah, when the group ring will be infinite dimensional, this may be infinite dimensional. Okay,
exactly.
So for finite groups at least, this will be finite.
It
works, but for infinite groups, it may not be as nice.
Is inequality tight?
You mean that there are examples? I'm pretty sure. Yeah, I'm pretty sure that there are examples where if you project, I'm not sure. I don't want to say anything because I really don't know. But there is a notion of what's called the minimal Stein string. I think it's tight. Because what we will construct
should be
is in
tight. You take an irreducible representation, you compress it to a one-dimensional space. It should be tight, right? Like
yeah.
it should come. Take the. Okay, never mind. I'll maybe construct an example and then.
I think maybe a more conceptual explanation for it is kind of, okay, maybe I constructed the Hilbert space here. You can take a larger Hilbert space and project, like do something extra without really needing. So you can have an order relation on these dilations, and the dilation I construct now is the minimal one, in a good sense. Like you cannot have a smaller dilation, I guess. I mean, this bound is not always equals, right?
Yeah,
sometimes this will be much smaller.
I understand, but there are cases where it cannot be improved.
Yeah, but Michael thinks that there are cases where it's shown that it has to be equal, and we will also see when exactly this is equal in the construction.
I think that if you take an irreducible representation of a group and then just take the compress it in the sense that Alon defined, take subspace, smaller dimension subspace, and take the projection on both sides, you can tweak the numbers such that you should dilate it in this amount.
Good. Okay, so let's proceed to proving the theorem. And I mean, the proof is very nice, but it takes some time to actually digest. So I did write it out and I will go through it. We have one proof accepted left, so I think we have some time. Okay, so as promised, I will try to construct a Hilbert space H hat from this is a vector space tensor product. Okay, I just take A and H and take a vector space tensor product of it, not Hilbert space, not anything. And now I want to build a Hilbert space out of it. So I start by defining a sesquilinear form.
Wait, what do you mean by this product being vector space, whatever? What does this?
So A is an algebra. Mm-hmm. But so in particular, it is a vector space.
I see. So you're viewing A as a vector space.
Exactly. I mean, yeah, like you take a Hilbert space and you take a C-star algebra, there's no good notion of tensoring them except just as vector spaces. Yeah. Okay. So I take this tensor, but now I want to define a form on it. So I define this form on pure tensors. So A here will be an algebra element and C a vector. I define it in the following way. And the interesting fact is that the definition of this sesquilinear form involves our UCP map. Okay, so yeah, everything here is anti-linear on the first coordinate and linear on the second coordinate. And so this guy, you can indeed see that we can extend it by sesquilinearity to all. I mean, we can extend it to all of the tensor pool. Okay, I mean, this definition looks a bit strange, but this is some sesquilinear form which we define, which involves both the algebra structure, the UCP map, and the Hilbert space structure of H. But the problem is now we want to construct a Hilbert space, right? We need to check this is a positive form. And the positivity will exactly require us to use the positivity assumption of our map. And so how do we check positivity? We take some non-pure tensor and we evaluate the inner product with itself. And if you extend linearly, you get the following expression. Okay, and I need to convince you why this is greater or equal to 0. Okay, define A to be the matrix A1, A2, till AN. 0, 0, yeah, 0 elsewhere, and this is a matrix over the algebra A, right? I'll denote the algebra with a script. Great. Now notice that the matrix A star A, the coordinates of this matrix are exactly A star, AI star AJ, right? But this is a positive matrix. By definition, it's like it has a square root, right? And so we also know that phi n of A star A, this guy is positive as a matrix in some mn of BH, right? And this guy is exactly, if we want to write it out, yeah, I will draw over to here. This is like writing Xi, let me put a bar, and then phi n of A star A, Xi bar, where the inner product here is in the direct, is in h to the n. Okay, and Xi bar is like the vector containing C1 till Cn. Okay, and by assumption, this is positive. Okay, so this is some kind of like a play which results in our sesquilinear form indeed being positive because we assumed that phi is positive, is completely positive. Okay. Okay, so we have what we constructed up till now is some vector space with a positive semi-definite form, but it might have a kernel, right? I didn't say that if your norm is 0, then you are 0. So let's divide out by that. And we look at, so what is n? It will be the tensors which have inner product 0. And observe that by like a Cauchy-Schwarz argument, you can show that this is the same as x. Okay, maybe let me write it above. Using a Cauchy-Schwarz argument, you can show that this is the same as x in this tensor product, such that for any y in this tensor product, we have x, y, 0. Why? Because you have kind of a Cauchy-Schwarz, which says this is less than xx, yy, square root, I think. Given that they are positive, whatever, yeah. No, they are positive, we just proved it. But if xx was 0, then this is 0 and this is 0 also. I mean, the definition is here, it's not so clear that this is a linear subspace, but by defining it here, which is really like what usually, say, number theorists will call the kernel of the quadratic form, it is clear that this is a linear subspace, and so we can mod out by it. Okay, and so we get a linear subspace of this guy, we can mod out by it, and we exactly modded out by those which have inner product 0, and thus this form also passes down to this quotient, and you can complete it to get a Hilbert space. Okay, because in this quotient, this form is already strictly positive definite. Okay, so this construction up till now was quite strange. We defined some form and showed it's positive, but not definite, and we quotiented out by its kernel, and then completed this guy to get a Hilbert space. Okay, so quite a lot of non-passages. But then I claim that you can embed H inside H hat as follows. Okay, because I mean, you can compute that this guy, as we defined it in the new Hilbert space, this is just the norm of Xi in the original one, because this guy is something like Xi, phi of 1 star 1, Xi, and this is 1 because phi is unit. This is just how we define. So we get an isometric embedding of H inside this guy. Okay. Up till now, we didn't talk about but our goal is to get a star homomorphism into here, right? So we now want to let A act on H hat, meaning we get a star homomorphism from A to H hat. How do we do this? We act in a trivial way, right? We have, on pure tensors, we'll just do this. And by the way, the construction is quite involved. Do you have any questions you want me to clear up? Okay, either it's, okay, I will continue, but just stop me at any point. And so I constructed this Hilbert space, and I now want to define an action of this C-star algebra on it. And to check that this guy, okay, this guy extends linearly, like to an action of A tag, but we need to check that this action is bounded and it will also show it's well-defined. And so this involves an extra little calculation, which also, I mean, this inequality uses Phi's UCP, but I don't think it's good to go into a technical thing. But at the end of the day, this kind of rule gives you a star homomorphism from A into BH hat. Okay, this gives you an action of A on BH hat. And then I claim that this action restricts exactly to our original phi. Why? Let me calculate it very briefly, just to make you happy, or not. But so what was our embedding? I mean, I look at one tensor C. So C now will be always in H, right? Our embedding of H inside H hat was just identifying it as one tensor the vector. So this is how we use calculations on it. And one tensor C, and and so we have the projection onto H. We have pi of A. We have projection onto H, and again, one tensor C. But this will be the same thing as just one tensor C. So I move this guy over here. But I mean, one tensor C are exactly in the image of this projection, right? This projection is onto the copy of H inside H hat. And we get this. And here it will be, again, pi A of one tensor C for the same reasons. I mean, these projections do not do anything, not affect. And this will just be something along the, and this guy will just be A tensor C, just by this definition, right? This is how we act on pure tensors. And so we end up with C, phi of A, and C. I mean, this is A times 1. This is just the definition. This is how this is by definition of the inner product on the larger Hilbert space. I mean, this is all artificial work just to get that the action on the larger Hilbert space when compressed to the lower one and considering inner products in this larger one gives exactly the same thing as our original thing. Yeah, the main point is somehow the assumption of complete positivity allowed us to, first of all, really state that this guy, the sesquilinear form we defined is positive. And second of all, it also involves, it gets involved in this little calculation, which says that the action we defined is well defined. Yeah, but this basically ends the proof. And again, this is maybe reminiscent to some of the experts of your like usual constructions of positive definite functions on groups, because it is this thing just generalized to another setting. Okay, I will move on. Yes.
Alon, I just want to remark that in some sense, this is very nice because add the algebra, and on the tensor product, you act only on the algebra part, where it's the same as you said, it's like Cayley's theorem. Like you, like the group acts on itself. Here, the algebra acts on itself, and you tensor it with H, and on H, you do nothing. But the inner product is exactly where the UCP map gets inside. So the action is always the same, regardless of the UCP map, but the UCP map changes the inner product of the space that we generate. And this is how the UCP map gets inside.
Yes. So yeah, as Michael just remarked now, this was our initial observation that how we define this inner product on the larger space involved our original UCP map. And then the action was purely algebraic, with no relation to phi. However,
sorry, what action? What do you mean by the action?
So when I say action, it's kind of like paraphrasing, saying star homomorphism, because like I'm already quite used to thinking of a star homomorphism into BH as C-star algebras as saying a representation or an action of the algebra on the Hilbert space, right?
I see.
Yeah, just like in representation theory, you say a homomorphism from the group to GLNK is the same as an action or representation of a group on the ambient space. And so Michael remarked that the action we defined here only involved like the action A on H hat only involved like A itself, but how we define the inner product and as a result of also what we divide out with gives us a different Hilbert space each time and a different projection. But also so the observation like what Nati asked, I mean, this whole construction started from this vector space tensor product of A and H, and then divided out and completed by, but completing and dividing out dividing out can only decrease the dimension, or at least, I mean, okay, it's not a Hilbert space yet. It doesn't really have a dimension in the Hilbert space sense, but if everything is finite dimensional, we can only go lower than the dimension of A times the dimension of H, right? Yeah. So this is kind of a central observation, because now I'm going to jump back to Naimark. And now I want to kind of convince you, at least vaguely, how this very general phenomena reduces to, I mean, I hope you agree with me that, okay, people define these UCPs and then got this very nice classification result, which I think is natural but surprising, of course. However, it manifests itself in many situations, and this is one of them. And I want to convince you. So I will just remind that we had these. Here we have two players, but now I want to start proving it by first talking about just one player, okay? Because Steinstring doesn't deal with commuting UCPs. This will be an extra step. But my claim, so a lemma, I want for say a POVM on say H, and H is finite dimensional, and any auxiliary state in C to the K, where, okay, A is like from 1 to K, so K is the number of questions, okay? Any state,
number of answers in this.
Yes,
right?
so absolutely, yes. So here it's the number of, so kind of now you need to fix a player and fix a question and look at its POVM. I want to dilate this guy. So any state you choose in the C to the dimension of number of answers, we can, it holds, there exists some AA twiddle, a PVM on H tensored with C to the K such that, so this is like HA aux, right? Like this auxiliary Hilbert space, such that we will have, on H we won't do anything, tensored with this. Yeah, now I'm kind of switching a bit notation back to these bracket things. So it took me a bit of time to unravel this, but hopefully I will explain it okay. So the equation is as follows. Okay, what do I mean by this? Many of you probably know, but I needed some time to understand what I mean. Here it's like this guy is an operator on this tensor product, right? This one. Okay, and we're just tensoring the rank 1 projection onto this auxiliary state with the identity on H, right? This will be exactly this projection. Sorry? Michael.
Yeah, Alon, maybe just define this. We didn't define this Bryant-Ket notation, so maybe just say what this thing is.
Well, it's just the projection on the auxiliary vector. That's,
yeah,
maybe
the projection on space span aux.
Exactly, onto span aux.
well,
So this is like,
yeah.
So this is like just a random.
It's also restricting the dimension. It's not just a projection.
It's what, sorry?
It also takes you to a space of smaller dimension.
Yeah, it is a strict projection, a proper projection, yes. Like it projects from tensoring with C to the K back to H. Okay, and this is exactly like this is what is PH from back then. Back then, we just, I mean, in mathematical, without any bracket notation or whatever, we just had some embedding of H inside the larger Hilbert space and a projection onto it. So this will be the projection onto it, and you should think of
so
the
I
embedding.
think Alon on the right hand side, the rightest most aux, the bracket is vice versa, is the other way around, right? You want the projection on both sides. This is not a vector. This tensoring with aux. No. On this part you were right.
Like
on the
this?
other part. No. The other one. Yeah, the other one is. I think.
I have to confess,
Why
The other
is
one is
this
fine.
fine? Why you want the projection as well there? No,
but
maybe
it's
I
like kind of transpose.
No,
I mean,
no.
like.
No, it's
okay,
fine.
so I'm missing something. What is the right hand side?
This is also the projection. Both are the projection, just that I guess this is already a notational issue, I guess, that when you take the transpose of like bra, you get ket, I guess. I mean, no, I don't know how to explain it. Maybe Dorit, you know, like.
This is basically, the right-hand side is basically a unitary embedding in a larger space. You're adding.
You mean in this sense?
Well,
okay, yeah,
But I thought, Alon, you want projection on both sides. This is what you don't want the co-projection.
It's very confusing, but essentially it's like a projection on. It's first a unitary embedding and then project on that state, on that tensor product state to being the auxiliary state.
Okay, so you mean you take a vector in H, you attach to it the auxiliary state, and by that you embed it into H tensor C to the K, but you look only on the part of the space that is already the span, like the things from H tensor span of
yes,
Fox, right?
but A Twiddle can act on everything, right? A Twiddle needs to consider the extra dimension had.
I'm okay with okay with A Twiddle acting on this. Okay, so now I understand. Okay, so the process is take an element of H, attach to it aux, act with A Twiddle, then project to the space spanned by aux tensor all of H. This is the same thing as acting with AA.
Exactly.
Great.
I mean, yeah, this is, at this point, it's kind of, I mean, I'm less used to this bracket notation, so I don't think I'm the person to explain this, but as Dorit said, I guess our unitary embedding from before, this is H hat, or should be H hat, is just tensoring with some auxiliary state. The choice doesn't matter. And then this equation is just basically what we had from before. Sorry, I will scroll back and that. Okay, you can also view it as, I can also rewrite it in Dorit's language, where you say that V is the unitary embedding H inside H hat. Then you say phi of A is like V star pi A V, right? I mean, it's just a matter of whether you view H as inside H hat or with the extra added step of embedding it. I mean, yeah.
Okay.
Now it's much clearer. Yeah, now it's much clearer.
Okay, I still have a question, but can you go back to the...
Yes. About the...
Right. So yeah, so the thing on the right is an operator on H tensor C to the K, and the thing on the left is an operator on just H. So how can there's something?
You mean this?
No, Guy. Now let's read it. The operator on the right hand side takes an element of H and gives you back an element in the subspace of H hat, which is isomorphic to H. Right? You take an element of H, you attach to it an auxiliary vector. This now becomes an element of H hat.
Okay, where on the right hand side do you see that you attach an auxiliary vector to a given?
This is the rightmost operator. This is what confused me as well, Guy. The rightmost operator just tells you
operator takes a vector in the product and keeps...
No. It actually takes a product, an element of H, and attaches to it the auxiliary vector. This is what this operator does. Yeah. It is written in a peculiar way, but this is what this operator does.
Okay, I see. Okay,
yeah.
Fine.
I mean, how I kind of viewed it is I view the auxiliary state always as a covector, so as the projection, and then I take the tensor product of this projection and the identity operator, I get a projection inside the larger space. I mean, this is how I interpret it. But
yes, but this what was confusing me, because if you view it the way you did, Alon, you should have reversed the brackets. But the reason
this is the problem with mixing.
Yeah, the reason that the brackets are used in this particular orientation is because you think of your vector as given in H without not being in the large space. Think of it as in H, but then you attach to it the auxiliary part, you act with the operator from the large space with A twiddle, and then you project to the subspace, which is isomorphic to H. But
I see.
Projecting back to the subspace that is isomorphic to H, you can think of it as sending it back to H. So it's the same thing as acting from H to itself, but AA is something that acts from H to itself.
Yes.
I don't know if it's helpful, but this is how I see it.
Yeah, I mean, the best thing is everyone just choose how he wants to view it, but there's a good chance that everyone is confused because I switched notation suddenly. But this is, I mean, for me personally,
Alon, we don't really have to understand bracket notation now. Just the operator on the right takes a vector in H, and the tensor products it with the auxiliary vector.
Yes. And then the
operator on the left just projects, does nothing on H, and on the right hand side projects on the auxiliary vector.
Yes.
And actually then also applies the trivial isomorphism from that to H.
Yes, exactly. Absolutely, yes. But I mean, the main point here, what the small difference, I mean, I still didn't tell you why this is exactly Stein-Spring dilation, right? Because, I mean, why is this Stein-Spring dilation? Because here we have a map phi from C to dk into BH, right? This is like the, given a POVM with k elements, we constructed this UCP, right? And this gives us H hat, the dimension of H hat will be less than k times the dimension of H, right? Our construction had this. So because all finite dimensional beings are isomorphic, we can, without loss of generality, assume that H hat, okay, maybe you need to take a larger space than H hat just to be dimension exactly k times then H. And then you can assume without loss of generality that the model is the tensor product model, and the embedding is just by tensoring with this specific auxiliary state. I mean, up to this equivalence, it's the same. You may complain that this equivalence is not, I mean, what would you do to actually, I mean, compute a twiddle? And you can do this, but I mean, the proof of this lemma doesn't need to go through Stein-string dilation. There is a much simpler proof in the article, which I confess I didn't read too much because I am really confused by bracket notations in general. But I mean, this is, I think, a nice example of how Stein's, like a operator algebra notion manifests itself. Just that in the finite dimensional case, you can talk about it in many different languages, and this is one of them. The only thing we need to notice here is that Stein-string dilation guarantees that the Hilbert space we constructed has dimension less than the tensor product. So you can assume without loss of generality that it's the tensor product, and the embedding is the one Michael and Guy and Dorit mentioned, which is just tensoring with the auxiliary state. Okay, I think I will
declare the time is over.
Yeah, exactly. That's all. Thank you. Sorry. Yeah, I mean, I didn't show the last part, but I think that's enough for a day. Count the last part as a discussion, which we usually have. Okay, thank you.
Thanks, Alon.
Thank you.
So what